Hello, welcome to this video. Today we're going to do this problem. So we want to find all natural numbers n such that n factorial is a bigger power than 2 of a natural number. Actually, I should mention a bigger power than 1. So we have this problem. So basically what it means is we want to find all natural numbers n, and by natural I mean positive integers, not including 0, such that the number n factorial can be written as some natural number 8, some natural power b, where b is bigger than 1. Okay, so we basically want to find all natural numbers n such that these numbers a and b, such that b is bigger than 1, exist. So let's solve this. So let's break it down into cases. First of all, an obvious case, n is equal to 1. This is obviously true for this because 1 factorial is 1. 1 can be written in an infinite amount of ways as a power, right? It's 1 squared, it's 1 cubed, it's 1 to the 2023, it's whatever you want. So if I pick, say, 1 to the power of 7 or something like that, then it works. So n equals 1 works. Now, for n bigger or equal to 2. Okay, so let's notice something that now follows from this equation. So if I have some prime number p that is smaller or equal to n, then that occurs if and only if p divides into n factorial. It's true. I'll let you think about it why it's true, but it is. But that's obviously if and only if p divides to a to the b, because a to the b is equal to n factorial. And so that means that that happens if and only if, because p is a prime number, that's if and only if p divides to a. But then that's if and only if p to the b divides into a to the b. Right? Because if this is true, then p divides into a to the b, and then p divides into a. And if this is true, then obviously this is true. And then that's if and only if obviously p to the b is equal to n factorial is divides into n factorial, not equals. And then from this it follows that p squared divides into n factorial since b is bigger than 1. So we got that if p, and so last thing, because p is a prime number, then if we think about how can p squared divide into n factorial, then let's think about the list of numbers. Okay, we have 1, 2, then the first time n factorial will be divisible by p was when it hits p, then you get to p plus 1, p plus 2, and so on, and they're not divisible by p until we get to 2p, right? And only after the n is equal to 2p can p squared divide into n factorial. So from this we can actually say that 2p smaller than or equal to n. So if some prime number is smaller than or equal to n, then 2 times that prime number is also smaller than or equal to n. But now let's notice something. So there is this cool thing that if a number m is bigger than or equal to 2, then there is some prime number p that is between m and 2m, strictly in between them, 2m. This is a true fact, and we'll use it here. So let's take, first of all, actually n has to be bigger than or equal to 3 for this case. But you can see how n equals 2 also doesn't satisfy this, because if n is equal to 2 and factorial is equal to 2, then that's obviously not a power bigger than 1 of a natural number. So, if n is equal to, so now let's take m as the ceiling of n over 2, and now if n is bigger than or equal to 3, then indeed the ceiling of n over 2 is bigger than or equal to 2. And from this we get that there is some prime number that is bigger than floor of n over 2, but yet that same prime number is smaller than 2 times the floor of n over 2. And we know that the ceiling of n over 2 is smaller than or equal to if I replace here n with n plus 1. So if I replace n over 2 here with n over 2 plus 1, right? This thing, ceiling of m, smaller than or equal to m plus 1. Wait, no, it's actually strictly smaller than m plus 1, because the ceiling of m, right, take the ceiling of 2, it's 2. Take the ceiling of 2.001, that's 3, right? Yeah, and that's strictly smaller than if I add 1 to this inside here. Yeah, 1 plus 2.001. Yeah, so this is actually strictly smaller than this. So actually this is strictly smaller than if I take 2 times n over 2 plus 1, that's n over 2. So you might be thinking, well, we're trying to get p smaller or equal to n. How does p smaller than n plus 2 help us? That means p is smaller than or equal to n plus 1. Well, think again. P is smaller than this. This is a natural number, which means that p is smaller than or equal to this number minus 1. And this number is strictly smaller than this number, n plus 2, which is also a natural number. This natural number is smaller than this natural number. So this is smaller than or equal than this minus 1. So this is smaller than or equal than n plus 2 minus 1 minus 1. And that is equal to n. You can think about it as if p was n plus 1, then this natural number here, 2 times ceiling n over 2, would be like squeezed in between n plus 1 and n plus 2. And it couldn't be actually a natural number. So p actually is smaller than or equal to n. Which means that we get the 2p smaller than or equal to n. That means that n is bigger than or equal to 2p, which is strictly bigger than 2 times the ceiling of n over 2. But the ceiling of a number is bigger than or equal to that number, which means that this is bigger than or equal to 2 times n over 2, which is n. So n is bigger than n. That's a contradiction. So for n is bigger than or equal to 3, it's impossible. For n is equal to 2, you can clearly see why it's impossible. So the only solution here is n is equal to 1. And finally, that's it. If you want more content like this, please subscribe to my channel. I'll be uploading more interesting problems and things like this in the future. And finally, that's it.